Hello everyone, welcome to a new lecture of microprocessor. You already know about microprocessors. Most microprocessors allow normal program execution to be interrupted by some external signal or by a special instruction in the program. And in response to an interrupt, the microprocessor stops executing its current program and calls a procedure which services the interrupt. In this video, I am going to introduce you to the 8086 interrupt types. We'll show you how the microprocessors in the 8086 family respond to interrupts and different kinds of interrupts, priorities of interrupts, and how interrupts are used in a variety of applications. These are some book references that you can follow for better understanding. At first, we have to know what is interrupt. The meaning of interrupt is to break the sequence of operation. Interrupt is a process when a normal program execution to be interrupted by some external signal or by a special instruction in the program. While the microprocessor is executing a program, an interrupt breaks the normal sequence, diverts its execution to some other program called interrupt service routine, or in short, we can say ISR. After executing, control returns the back again to the main program, right? So what happens when a microprocessor is interrupted? When microprocessor receives an interrupt signal, it suspends the currently executing program and jumps to an interrupt service routine to respond to that incoming interrupt. Interrupt service routine actually stores the instructions what actually CPU has to perform when CPU will be interrupted by any of the interrupts. You can say interrupt service routine is a guideline for CPU to give service to the interrupts to solve them. There are many kinds of interrupts and each interrupt will have its own interrupt service routine. And again, after finishing the interrupt or interrupt program, automatically it will return to the first program or the program that has been interrupted before and start execution from where it was left. The processor can be interrupted some following ways. It can be interrupted by an external signal generated by a peripheral such as keyboard, mouse, printer, monitor, etc. Again, interrupt can be by an internal signal generated by a special instruction in the program or by an internal signal generated due to an exceptional condition which occurs while executing an instruction, and that I am going to explain these later. Now, classification of interrupts. Interrupt can be primarily classified into two main types. Those are hardware and software interrupts. Again, hardware interrupts can be of maskable and non-maskable interrupts. And there is a total of 256 types of software interrupts possible in 8086 microprocessor. Now, first one is hardware interrupt. The interrupts initiated by external hardware by sending an appropriate signal to the interrupt pin of the processor is called hardware interrupt. The 8086 has two interrupt pins. One is INTR, this is pin number 18, and another one is NMI, or we can say non-maskable interrupt pin, and it is pin number 17. The interrupts initiated by applying appropriate signal to one of these pins are called hardware interrupt of 8086. Hardware interrupts used to handle external hardware peripherals such as keyboard, mouse, hard disk, floppy disk, DVD drivers, printers, keyboards, etc. For example, every keystroke of keyboard generates an interrupt signal, right? Interrupts can also be generated by other devices to indicate that some event has occurred. Suppose like printer, when you give a print command or printer sends an acknowledgement to the CPU, it indicates that yes, some event has occurred there. These are called hardware interrupts. Now, hardware interrupt can be of two types. Okay, maskable and another one is non-maskable. Now I'm going to explain what are these two types of interrupt. Our processor has the facility for accepting or rejecting hardware interrupts. Programming the processor to reject an interrupt is referred to as masking or disabling the interrupt. Okay, and again, the programming the processor to accept an interrupt is referred to as unmasking or enabling. In 8086, the interrupt flag, IF flag, can be set to 1 to unmask or enable all hardware interrupts. And IF flag is cleared or set to 0 to mask or disable a hardware interrupt, except the interrupt come into the NMI or non-maskable interrupt pin. The interrupts whose request can be either accepted or rejected or can be delayed by the processor are called maskable interrupts. And the interrupts whose request has to be definitely accepted, those cannot be rejected and cannot be delayed by the processor are called non-maskable interrupts. So we can easily understand that maskable interrupts are of less prioritized than non-maskable interrupts. Whenever a request is made by non-maskable interrupt, the processor has to definitely accept that request and service that interrupt by suspending its current program and executing that particular interrupt service routine for that particular non-maskable interrupt. In 8086, processor, all the hardware interrupts initiated through INTR pin, that means pin number 18, are maskable. Okay, any kind of interrupt that comes through this INTR pin are maskable interrupt, and processor sets it by clearing interrupt flag. Okay, when processor don't want any kind of interrupt, it just clears the interrupt flag to 0. The interrupt initiated through NMI pin and all software interrupts are non-maskable. The programmer cannot control when a non-maskable interrupt is serviced. The processor has to stop the main program to execute the non-maskable service routine. The programmer can choose to mask specific interrupts and re-enable them later in case of maskable interrupts. Okay. Uh, there are some example of non-maskable maskable interrupts. Non-maskable interrupt, suppose non-maskable interrupt pin or NMI pin is used when during power failure. Okay, during critical response time, non-recoverable hardware errors, or during memory parity errors. If these interrupts occur, processor cannot reject or delay them. Rather, it has to accept them instantly and respond to them instantly. Again, there are some examples of maskable interrupts, interrupts from mouse, keyboard, or other peripherals. These interrupts can be rejected, accepted, or delayed for a while. The software interrupts are program instructions. Okay. Now, software interrupts. These instructions are inserted at desired locations in a program. While running a program, if software interrupt instruction is encountered, then the processor initiates an interrupt. The 8086 processor has 256 types of software interrupts. The software interrupt instruction is INTN. Here, N is the type number in the range 0 to 255. Suppose I am saying interrupt number 21, then the value of N is 21. Or I can say interrupt number 01, that is the value of N is 01 or 02 or 10. Okay. Each interrupt has its speciality or its particular instructions or particular tasks. So an 8086 interrupt can come from any of the three sources. One source is an external signal applied to the NMI or interrupt pin. An interrupt caused by a signal applied to one of these inputs is referred to as hardware interrupt. A second source of interrupt is execution of the interrupt instruction. That means INT. This is referred to as a software interrupt. This is INT that I have explained in this slide, that INT 21, INT 10, INT 9. These are software interrupts. The third source of an interrupt is some kind of error condition produced in the 8086 by the execution of an instruction. Let me give an example. An example of this is the divide by zero interrupt. You know, if we divide any value by zero, then it will produce a result of infinity. Okay, the quotient will be infinity. So it is an error. If we attempt to divide an operand by zero, the 8086 will automatically interrupt the currently executing program. There are also some interrupts like this type, that is overflow interrupt, uh, type 1 interrupt, type 2 interrupt. Okay, these are actually called predefined interrupt, and these interrupts are predefined by our 8086 processor. Now interrupt vectors and vector table. All interrupts that I have explained, those are hardware interrupt, software interrupt, etc., are mapped into a memory area called the interrupt vector table, especially software interrupts. The interrupt vector table is usually located in the first 1 kilobyte of memory segment from 0000H to 003FFFH. The purpose of interrupt vector table is to hold the vectors that redirect the microprocessor to the right place when an interrupt arrives. Every interrupt has their, we already know that every interrupt has their specific interrupt service routine, and every interrupt service routine, the first address of that interrupt service routine is stored in this interrupt vector table. So there is another term, that is interrupt vector or interrupt pointer. What is that? Interrupt vector is a pointer to where the ISR is stored in memory. Every ISR is there are stored some kind of instructions, right? So any kind of instruction, we know we have to find out the CS and IP value. The starting address of an ISR is called interrupt vector or interrupt pointer. We have to remember these terms. One is interrupt vector table, where the starting address of the ISR is stored, and in each interrupt vector table, in vector table, each starting address of the ISR is called interrupt vector or interrupt pointer. So that's why the table is referred to as an interrupt vector table, or we can say interrupt pointer table. We know to execute any kind of instruction, we have to fetch them from core segment of the memory by using CS, core segment registered value, and offset IP value. We also know that CS, core segment register, and instruction pointer, these registers are 16-bit, or we can say 2-byte registers. 4 bytes are required to store the CS and IP values. For CS, there is 2 bytes. For IP, there is 2 bytes. So total, we need 4 bytes. So 4 bytes are required to store each interrupt service procedure. The interrupt vector table, that's why, can hold starting addresses for up to 256 interrupt procedures. Why 256? Because we know CS 2 bytes, IP is also 2 bytes, so total 4 bytes. And if we do a simple multiplication, that is 256 into 4, that is 124 bytes. And this is 1 kilobyte memory location. And this 1 kilobyte memory location, it can be easily understood that 256 type of vectors, type of interrupts can be stored there. We don't store the interrupt service routine, but rather than we store only the starting address of those interrupt service routine that are somewhere kept in our memory. Okay. Here, one thing I like to mention, that IP value is of the lowered. Okay, there is 4 byte total, so 2 word. The lowered is the IP value, and the higher word is the CS value. Again, each double word interrupt vector is identified by a number that is from 0 to 255. I have already mentioned that type 0, type 1, type 2, type 21, type 35, type 37, type 255, etc. So Intel calls this number type of the interrupt. I have previously mentioned that these 1 kilobyte of locations, that ranges from 0000H to 003FFH. And we know what should be the logical address to address these 1 kilobyte of locations. These are the logical values. So CSIP for this interrupt vector table can be 00000, that is the value of CS, and that is the value of offset. 2, it is the value of CS, I mean the starting address of the core segment register, and that can be the value of offset. So when we do some physical, you know that how to calculate physical address, right? So when you calculate physical address by these logical address, you will get the particular memory location to serve that ISR, or to fetch that inter-service routine, or to fetch that instructions that are needed to solve that kind of interrupts. This is the interrupt vector table. This figure shows how the 256 interrupt vectors are arranged in the table in memory. Note that the instruction pointer value is put in the lower of the vector I have mentioned earlier, and the core segment register is put in as the high word of the vector. Okay, so each double word interrupt vector is identified by a number 0 to 255. The lowest 5 types of interrupt, that means type 0, type 1, type 2, up to type 5, these are dedicated to specific interrupts, such as type 0 is for divide by 0 interrupt, type 1 is for single step interrupt, there is a non-maskable interrupt that is of type 2, type 3, and type 4 that is of overflow interrupt. Later in this, in my next video, I'm going to explain the operations of these interrupts in detail. Again, interrupts from type 5 to type 31. Okay, these 27 interrupts are reserved by Intel for use in more complex microprocessors, such as we are studying 8086, right? We will later study 80286, 80386, 80486. These are the updated microprocessors. These are more complex, more latest microprocessors, right? So type 5 to type 31, these 27 interrupts are reserved for those complex microprocessors. Okay. In later chapter, we will describe those microprocessors also. And the upper 224 interrupt types, that is from type 32 to type 255, the last one, are available for user to use for hardware or software interrupts as we require. Okay.